let's get started. If you still have your homework, wait till after lecture to bring it up and put it on the pile. Today we're going to review the properties of networks of nanostructures. We've talked over the past few lectures in general about how to form networks, meaning two-dimensional or three-dimensional assemblies with some degree of organization. And today, just in one lecture, we're going to talk a bit about the electrical, thermal, and mechanical properties and how they scale based on the interactions among those structures. First, the announcements I have. If you haven't already signed up for a meeting on Thursday, please do so. I've heard from some of you. I'll reply to your emails that you want a different time, and I'll certainly accommodate that. Also, our presentations next Monday evening will be here from 6 to 9 p.m., and there'll be no lecture on Monday. If you can't make it during that time or can only make it for part of the time, I'd like you to let me know in advance. Otherwise, I'd hope that everyone could be here for all the presentations so we can all provide feedback to all the presenting groups. Also, as I said in a couple places, just to repeat it here, formally, due to the requirements of having things due before exams, your reports are due Tuesday, April 20. However, if you want to turn them in as late as Friday at 5 p.m., you won't be penalized. So that's entirely up to you. And I was going to ask for the people who are taking the GCC, if anyone is here who's taking the GCC. Do you want to have maybe kind of a review session in the evening late next week? Okay.
No. If there's a yes, if there's a couple of yeses, we'll do it.
Just we can, for example, talk about the exam, the midterm exam, and any questions you might have about what the exam will be all about.
When? Later next week?
Yeah.
Thursday or so? Okay, sure.
So, in principle, we've talked about networks of structures already, and here we see the chart for organization of carbon nanotubes that we've seen a few times before. And by a network, I simply mean an assembly of structures where the properties of the assembly are determined by transport through the individual structures and connections between and among the structures. And transport can mean electrical, it can mean thermal, it can mean mechanical. So electrons, phonons, or vibrations, and load. And if we don't have, say, the ideal case of an individual structure spanning a gap, which could be an electrical wire or a thermal wire or a mechanical wire, in all the other cases we're in principle going to have some combination of effects, and we're going to see scaling of properties based on those effects. And today we'll just be able to touch on a few examples of how these effects govern the electrical, mechanical, and thermal behavior of assemblies of structures. And if we hold to our example of carbon nanotube materials, you can imagine that if you had a vertically aligned forest, in the ideal case, the properties of that vertical forest would be just determined by the properties of the individual structures multiplied by the number of structures in the forest. But indeed, there is some imperfection in the characteristics. There is, for example, contact between different structures. You could imagine transport going through one nanotube and jumping to another. Also, the possible lack of continuity of the individual tubes within the forest might affect the transport. Another example is if we took, for example, a tangled film of nanotubes or nanowires. There you can say a case where the transport is definitely less continuous. And to go from one side of, say, this wafer to the other side, or more realistically, even if you had, say, a micron scale patch of structures, to go from one to the other, you're going to have to jump through a number of structures and also from one structure to the other. And in larger scale applications, for example, these large scale sheets, these are essentially just very large tangled films. And also if we took the dispersions that we made a few lectures ago and mixed them, for example, in a polymer, you would also have a network property. And this was one of the first applications of carbon nanotubes to make plastics have electrical conductivity. Not metal-like conductivity, but conductivity that would be enough for example, electrostatic discharge or electromagnetic shielding. So, these are all examples of different, generally types of networks. And today we'll mainly break down into the idea of what the properties of one of these films would be. And we'll talk a lot about carbon nanotube networks, but I think there's some generality to other types of structures depending on their geometry and their interactions. So here's a bigger picture of a tangled film of nanotubes grown on a substrate, and just by looking at this picture, we can kind of see that if you're over here and trying to get the other side by following the nanotubes, a lot of different types of interactions are going to be important. We're going to be interested in the general topology of the network, the diameter of the tubes, how they connect with other tubes. You can see here that there are some cases where it seems the tubes are branched, and these in a general sense could actually be branch structures that branch during growth, or they could be, for example, bundles of tubes and the bundles are splitting during the growth. The length of the individual segments is going to be different. The conditions of contact are going to be different. Some might be in better contact than others, but we're going to have a number of those interactions happening as we cross from one side to the other. And the importance of different types of interactions is going to be different depending on the property we're considering. But by and large, the way of characterizing these types of network is to make sort of bulk estimates. Characterize the number of nanotubes you have and say the average length of the nanotubes between contacts and the type of contacts, and then try to relate the scaling of bulk properties such as electrical conductivity to some of those characteristics. And one of the most basic elementary things that's done is just say plotting the conductivity of the network as a function of the volume fraction of nanotubes, or the area fraction of nanotubes. And you could imagine that conductivity would get higher as you fill the space with more structures. And we'll see some more specific aspects of that in a few slides. So today then we'll talk about the general concepts and dominant behavior of these networks of structures. We'll talk a bit about electrical transport, particularly in relation to percolation theory, which is a basic theory that just describes how the electrical transport through a network scales as you scale the characteristics, and particularly the volume fraction of structures, or volume fraction of filler you have in a simple area. And then we'll talk a bit about thermal transport and mechanical properties. And at the end, if we have time, we'll talk about methods of joining structures. Incidentally, last year this lecture was about 2.5 lectures, so given our limited time, I've tried to condense it down, and I've put a bunch of the extra material in extra slides. Overall, the problem sets are over. We're all working on the project. I don't expect you to follow up on a lot of readings on this material, but just for reference, I have a bunch of optional papers that you could look at now or later if you want, in terms of talking about the theory and applications of electrical network properties, thermal network properties, mechanical network properties, and also on aspects of joining, particularly methods of joining carbon nanotubes using electron and ion beams to essentially zap them to move the atoms around and weld them together. So both for our course material and also for the GCC, I must say that we're not going to have a lot of coverage of this, but I wanted to address the topic for us all to be able to discuss it today. So I'd say the goal of having a network of structures is to achieve the properties of individual structures at larger scales by assembling those structures into a two-dimensional or three-dimensional network. Maybe that goal is not a surprise, but there are certainly some challenges and important aspects, because it's never, almost never the case that you can get that individual structure property by just having a number of structures together. And also other goals might be to achieve combined properties of different types of structures. We won't touch on this so much, but this is also an emerging interest. For example, if you wanted to achieve characteristics of a metallic material and a semiconducting material, or achieve characteristics of two types of semiconductors that, say, have different colors, you could simply try to mix them in a network and achieve some hybrid property. But there are a lot of practical aspects that dominate and govern the performance of a network of structures. For example, the performance is dominated by the architecture and morphology of the network. So are the tubes or are the structures aligned or tangled? That's certainly going to have a big effect on the way transport occurs through the network. It may determine what is dominating the transport, and also whether the transport is different in different directions. Just as you would imagine an aligned fiber composite at the microscale having anisotropic properties, a network of aligned structures at the nanoscale would also have anisotropic properties. Certainly the geometry or the shape of the individual structures has an effect. comparing nanorods or nanotubes to nanoparticles. The behavior, say, of conductivity as a function of the volume fraction is going to be very different if you're adding pieces that are very long and narrow and sort of hooked together easily to individual particles. And also the intrinsic properties of the individual structures are important. We'll see cases where the transport is dominated by the characteristics of the structures, and we'll see cases where the transport is dominated by the contacts between the structures. And that gets to the fact that the interactions between the structures and also between the structures and the host material are important. So in some cases, maybe we just have a film of nanotubes or nanowires without any matrix, say without a polymer surrounding them. In other cases, we might have them in a polymer matrix to, say, stabilize them or to transfer load more uniformly. And it turns out that, for example, if there is a little bit of polymer between a pair of nanotubes, that could dramatically affect the contact resistance if you're considering electrical transport through the network. Likewise, the strength of bonding between nanotubes and a polymer has a big effect on the final properties of that composite. And also, for example, in the case of thermal properties, the interface, the matrix can also, for example, involve itself in phonon scattering as vibrations go down a tube. The fact that it's mechanically coupled to something around it can also dramatically affect the properties of it. And all these, sort of geometric and topological and contact issues complicate characterization. It doesn't mean you can't characterize one of these materials, but there are a lot of different geometric and other aspects to examine if you wanted to, say, get a precise relationship between the structure of the network and its performance. And we'll see an example of how, for example, studying the size effects of even just the length of a film of tangled nanotubes can get some insights into the scaling of the properties later on. So there are a lot of applications of networks of structures. I wish we could talk about some of these in more detail, but just to review a few of them, one of them, the major and first applications of carbon nanotubes and of, for example, metal nanowires is making conductive plastics for the application of electrostatic discharge and shielding. And in fact, I think one of the first applications of carbon nanotubes over like 10 to 20 years ago was they've been added to the plastics in vehicle interiors, for example, inside the interior door panel, and also have been added to plastic car mirrors. And in the case of them being in a piece of the car interior, they actually discharge static shocks from your body if, for example, you're in a dry environment like in the winter and your rear end rubs on the seat and you build up some static charge. Touching the door frame discharges that without, for example, letting you later get a shock when you touch the metal outside of the car. That's really what's going on. And in the case of having nanotubes in plastics for the mirrors, in fact, in the manufacturing process, a voltage is applied to the mirror, and because the mirror has a certain amount of electrical conductivity, you can actually charge it, and then the paint molecules get electrostatically attracted to the surface, and that lets them conformally paint the surface of the mirror. And that was started, in fact, many years ago. And now, as we get more into understanding the real, electromagnetic properties of nanotubes and other structures, there are a lot of emerging applications in electromagnetic shielding or RF shielding. Often some kind of military things like putting films of carbon nanotubes in composites for making planes invisible in radar. And specific characteristics of single-wall nanotubes and their high-frequency properties are becoming very interesting for that, for military applications. There are a lot of applications in thin-film electronics. You could just imagine, as you may have seen, a lot of work in flexible electronics and in thin-film transistors. And in cases where maybe we don't need nanoscale transistors, but we want to create new electronics in, say, flexible formats or in dimensions that are necessary, for example, for transistors for displays, having these tangled networks of structures with transparency and conductivity or interesting semiconducting properties is useful for these types of emerging electronics. There are also a lot of applications in strain sensors and chemical sensors, as well as in energy conversion and storage devices. All the applications, for example, that consider using carbon nanotubes or carbon nanotubes and oxide nanostructures as electrodes or catalyst supports for batteries and fuel cells, for example, to some extent rely on the network properties. You need some bulk assembly of the structures, and then the net electrochemical or electrical property of that assembly is going to depend on their network properties. So there are many examples of these in the literature, and intimately the ability to sort of design and optimize those materials depends on how the properties of the structures add up into larger numbers. So first we'll talk in a bit more detail about the electrical properties of networks, and the main thing that governs the electrical properties of a network is what's called percolation. And percolation means if you start out with, say, an empty plate on the table and you start adding pieces to it, you'll see that the conductivity measured from one side to the other is going to change as you add more conductive things to the inside of your plate. Imagine starting out with a plate and dropping sticks on it and trying to form a continuous path across that. And the specific phenomenon of percolation means that there's a critical concentration of things you've added at which the conductivity jumps dramatically. For example, the conductivity goes from being the conductivity of your starting material, 0 if it's just an empty space, to being some conductivity that is determined by the conductive path that you add. So if, for example, we had a space like this, and you started adding nanotubes to it in random places, then at some point you would have a continuous path that could go through, and that would determine the conductivity. And if you plotted the conductivity, say, call it sigma, as a function of the percent of nanotubes you had on your area, you would see some scaling like that, where there's some critical concentration at which the conductivity jumps, goes from essentially 0 to some finite value. And this critical concentration is typically 1% or less when you are adding structures that have a high aspect ratio, things that are long and narrow. And in a lot of these applications as well, there's a large difference in conductivity between what you're adding and what you have in the first place. So if you're, for example, adding carbon nanotubes to a polymer is essentially electrically insulating. It has a very, very, very low electrical conductivity, and the nanotubes are electrically conducting. So the transport through the filler dominates the electrical properties of the network. In the case of thermal properties, there's a bit of a different behavior. We don't see this phenomenon of percolation. Well, we do see percolation geometrically in that when you add structures, there's be some point at which you form a continuous path. But because the transport is dominated very heavily by scattering at the contacts, the things are a bit more complex. And we'll talk about the specific cases of that later on. And just to overview this here, as we said before, the interactions between the matrix and the structures in terms of phonon scattering also significantly affect the properties. If we think about mechanical properties, again, we have a case where adding structures to a host material is going to form some network that is then going to bear the load. And you have, for example, a lot less reinforcement when you have a discontinuous network versus when you have a continuous network. But because in most cases, for example, adding nanotubes to a polymer, you have load sharing between the nanotubes and the surrounding matrix, you can get a significant enhancement before you have a continuous path. And in fact, it's the interactions between the structure and the matrix that are going to dominate often over the connections between the structures. So we can think of this property, for example, the stiffness or the strength at low concentrations scaling by a rule of mixtures, where you would have a linear relationship, for example, between the, say, the modulus or the strength and the percent you would have in the material. There are limitations and extensions to this in a lot of specific cases. But in general, if you, say, took this to a limit of highly aligned structures, and highly organized continuous structures, we would find that the stiffness of the material can scale to near theoretical values, just as we saw for mechanical properties of individual structures. We would also see that the strength of the material is governed by the ability of the total material to isolate defects. So defects can now be defects in the individual structures, and also can be flaws in the interaction between the structures and between the structures in the matrix. So in this case, the kind of joining between the structures and also between the structures in the matrix is very important. And that gets to a lot of studies of the effect of the alignment of the structures or their intrinsic waviness, and also the morphology and structure of the joints. You could also imagine that materials may be very different in tension versus in compression because of the way the load is handled and whether the structures extend or buckle. So in the case of thermal and mechanical properties, we'll get to more detailed aspects of these points later on in the lecture. And in all these cases, we also want to think about what types of joints we have in a network like this. So we can break down these types of joints that we might have in a general network into the types that are shown on this slide. So, for example, if we just have structures that we've essentially thrown on top of each other or grown on top of each other, a lot of the joints might just be due to entanglement. And for example, these entanglements might be brought into contact by van der Waals forces. So we know from ideas of adhesion and attraction that there is some attractive force at these joints. But other cases, for example, we may be able to grow or fuse structures so they're branched. And we saw a couple examples in the synthesis section of how those branched nanotubes were made in templates. And there are also ways to control the catalyst in nanotube and nanowire growth to issue branching. And for example, you may have Y junctions or T junctions. And if you were pulling on a structure like this, it would be much stronger and have better transport than a case where you're relying on just physical contact between a pair of structures. And then we'll see at the end of the lecture that there are also ways that structures can be welded. For example, if you take two carbon nanotubes and hit them with an electron beam or an ion beam under the right conditions with the right energy, you essentially can knock the atoms around so you can cause the structures to form a weld, actually join them together into a monolithic structure. But for our purposes now, just suffice to say that this can be done, and we can envision that this will provide a different type of contact than either of these cases up here. Likewise, it's also possible to deposit a metal or another material at the interface between two structures and kind of solder them together. And another case in this category is, say, where we're coating the structures, kind of similar to soldering, but imagine now it's immersed in a polymer or something has been deposited all over the surface, and there the transport is indeed affected by this interface region we have in between here. So the nature of the contact between a pair of structures is going to have a lot to do with the characteristics of transport between them. And whether we're making composites or, for example, depositing thin films on our network of structures, these issues are very important and determine what the final properties are. And we could break down the categories on the previous slide into, for example, non-bonding contacts. And when there's not bonding between them, we can say that those joints are dominated by van der Waals attraction or van der Waals adhesion. And this could be bare structures in contact, for example, a pair of nanotubes, or it could be cases where you have a thin interlayer. That could be a polymer, or it could be a functional group on the surface of nanotubes, and could be a bunch of other things. We could also have cases where the structures are bonded, and they could be bonded directly to each other. Or there could be a thin interlayer, and you could have bonding through that interlayer. And in the case of polymers and nanotubes, for example, the bonding strength between the polymer and the nanotube, whether it's just physically associated or chemically associated, plays a big difference in the final strength of the composite assembly. And in all of these cases, whether we have a material in between the pair of structures or whether the structures are physically separated like so, there are important sort of rule of thumb separation distances at which electrical, thermal, and mechanical transport can occur. So in the case of electrical transport, certainly if you have good contact and or bonding between the structures, then you're going to have better electrical transport than when there is a physical gap between them. But due to the ability of electrons to tunnel, essentially jump across a small gap, the same phenomenon as we know from scanning tunneling microscopy, in a gap of approximately up to 10 nanometers, you can get electrical transport across a gap if you have a sufficient bias voltage across your network. In the case of thermal transport, you can still get transport across a gap, but that gap is effectively much less smaller. And there are a lot of complex issues beyond this, but we could say that, for example, within a range of 0 to 1 nanometers, the atoms can actually feel each other due to intermolecular forces. And if one atom in one structure, one nanotube, is vibrating, a nanotube that's close to it can actually feel that vibration because of the intermolecular attraction between the two structures, and you can transport heat by that method. In the case of mechanical transport, of course, if we're not in contact, then our ability to transfer the load goes down a lot. So we can say to first order, we really need the structures to be contacting one another to have direct load transmission. Those surface forces need to pull them together, or you need to have something gluing them together chemically or physically. So there are a number of different ways that networks can be made. We saw, for example, CVD growth before, and we can take what we know about dispersion, purification, and separation to consider that you can deposit networks of structures by a variety of methods. For example, by spin coating, by dip coating, for example, by the Langmuir-Blodgett method, or just by taking a surface and dipping it through a solution of structures. And if you have good adhesion and the process parameters right, you can pull it out and you can have, for example, a tangled film of nanowires or nanotubes on the substrate. And there are other methods that we'll talk about in a minute. For example, vacuum filtration, just directing the structures through a porous membrane onto a substrate. And you can also do things like print them onto substrates and, for example, just mix your structures into a host matrix, like we saw the example of a polymer nanotube composite film that was made by dispersion and then polymerization of those little polymer particles. So, in the case of carbon nanotube growth, one way to make a network is just to put the catalyst onto the substrate. And for example, by different growth conditions, we saw that we could grow a tangled film or an aligned film. And in the case of the conditions that, for example, give a tangled film where the nanotube density is lower, this would be a way to produce a network of tubes on the substrate. And you could imagine that the density of the catalyst, the growth time, would affect the topology of this network and would affect its final electrical properties. Also, for example, the purity of the atmosphere or the amount of amorphous carbon that's on the surface of the nanotubes might also affect the final transport. It might determine that contact resistance between one nanotube and another nanotube that is in this film. Another method, for example, that can be used to create a tangled film of structures, in addition to just spin coating and dip coating, is to, for example, filter a dispersion of structures by a vacuum method. So this is what's called vacuum filtration. So what's done here is simply you have a pot, like a glass bin like so, containing a dispersion of nanotubes or structures. So this is probably carbon nanotubes functionalized with a surfactant like SDS. And you have, this is another a diagram of a different apparatus that does a similar thing, but you basically, by applying a vacuum to the underneath of the apparatus, you draw the solution through a filter, and then you collect the structures on the top surface of the filter paper. So, for example, like shown here, you draw the water, for example, of the solvent through here, and you leave the nanotubes on top. And if you, for example, controlled the concentration of nanotubes in the solution and the time, the amount of liquid you drew through here, you could control the thickness of this film. And because you have a uniform pressure across this membrane, you can probably get pretty large area, quite uniform films. And also, for example, if there are impurities in the solution that are smaller than the nanotubes, and also smaller than the pores that you have in your filter, you could say choose the pore size, so you might be able to pull the impurities through and leave the nanotubes behind. And then after this, you could take this membrane out and you might be able to transfer the film to another substrate, and in often cases these processes use thin polymer membranes that can be dissolved in solvents. So in fact you could dissolve that polymer membrane away and have a freestanding film that you could then pick up and put on a substrate, or just print onto a substrate and then peel the polymer or dissolve it away. And here are different films of nanotubes made by this method, just showing the ability to control the density of the final nanotube network. And in this case, what they did is they filtered different volumes of solution. So they had the same concentration of solution in each case, and the one on the left was made with 7 milliliters, and then the one in the middle was made using 10 milliliters, and the one on the right in C was made using 400 milliliters. So you see the ability to kind of span different concentrations of structures just by adjusting the amount of time in this deposition process. And there are, in fact, commercial products now available that are dispersions of nanotubes that can be used to make these tangled networks. And one company that makes them is Nantero, and actually through another company, Brewer Science, you can buy a dispersion of nanotubes that can be spin-coated or vacuum filtered onto a substrate. And they've done all the pre-purification such that this material is now compatible with CMOS standards. So it's clean enough to go into a commercial clean room. And here are just some SEM images of devices that they've patterned taking from this film. So for example, spin coating this thin film, and then for example masking it with photoresist and doing plasma etching to define patches of the film that you wanted to keep and patches you wanted to throw away, and for example putting electrodes on the surface. And in fact, this is the type of material that this company is now using to make a memory based on thin films of nanotubes, just by actuating suspended ribbons of the nanotubes electrically. And while we just saw an example of tangled networks, you can also have anisotropic networks where the structures are aligned preferentially in one direction. On the left, we see examples of ribbons of single-wall nanotubes that were printed in a multi-layer process. So in this case, these researchers at Illinois used a method where they could get lateral growth of aligned nanotubes on a substrate, and then used a polymer stamp to pick up the nanotubes and put them onto electrodes in multiple steps. And you can see here the sort of tightly aligned ribbons. Here they're more loosely aligned ribbons. And here's a case where they didn't use aligned tubes, but they used tangled tubes and achieved a similar result. And likewise, this is just a picture of the silver nanowires we saw a couple lectures ago made by the Langmuir-Blodgett method, and we could consider this another network. If we measured the conductivity of this, we can tell that the transport would be dominated by the electrical characteristics of the wires plus the characteristics of the contact between the wires. There is certainly a continuous path across this distance, but we're going to have to pass through many structures to get to the other side. And in all of these cases, the configuration that you end up in matters a lot. And I just showed this example. We don't see the details of what this material actually looks like, but here's a case where they grew a mat of tangled nanotubes and measured its resistivity. So higher resistivity means lower conductivity. And then they compared it to the same mat where they pressed down on it. So they added some mechanical force, and that mechanical force pressed the structures into better physical contact. So just based on proximity between the structures, they press them down and they stick better. And they saw, for example, when they pressed this mat down, they had a significant increase in the conductivity, or a drop in the resistivity from a value of 8 milliohm centimeters here to about 2 milliohm centimeters. And then they compared the characteristics of this mat to the characteristics of a single rope of nanotubes, which in this case was an aligned bundle that they made by the similar process. And without knowing the details, we can see here that the characteristics of that was even better. So they were able to improve this by a further factor of 10, or show that where you had transport through the individual structures dominating or being better, then you had a better conductivity in the final material. So in all of these cases, the final configuration that you make is going to be important. And the geometry of the structures in that configuration is what's going to determine the transport pathway through the material. So here we just see a better picture of what I was sketching out before. And there are a lot of methods that we won't get into in how the transport through these networks is modeled. But in the simplest case, if we think about making a network as a process of dropping straight sticks or twigs onto a flat space, we could relate that dropping process to kind of like a checkerboard lattice. And if we go from a lower concentration of sticks to a higher concentration of sticks, there is going to be some critical point at which we can follow transport from one square to another, and we can reach a continuous path through this area. And we're going to see different behavior whether the sticks are unaligned versus aligned. In this case, there's no continuous path because there are always small gaps or larger gaps between the structures. And here, there is finally a continuous path through the structures. And here is a case where even though the structures are aligned, the fact that they are aligned prevents them from crossing over. And even though we have alignment in this case, there is no percolation. There is no continuous path of the structures through the matrix. And a difference between this model clearly and, say, real nanotubes is real nanotubes are going to be perhaps more flexible and curvy, and that would make the situation more complex. But these kinds of basic geometric models were what were first used to understand this kind of percolation behavior. And it's also possible, for example, to visualize this kind of transport by, for example, electron microscopy. And this is a picture of a technique where they built a little device consisting of a small number or a little tangle network of single-wall nanotubes between two electrodes. And because in the SEM you can view the surface, you can essentially see color or contrast related to charge on structures by charging these electrodes at different potentials, like negative 20 volts or positive 20 volts relative to ground. They were able to see the path of electrons through the material. And you, for example, see cases where they charge both electrodes here, or they just charge one electrode, or they just charge the other electrode, and then they subtract the results of the three cases, or subtract this and this from this, and you get an image showing the path of nanotubes that essentially participate in the conduction across the gap. So it's just kind of a nice picture of how the transport between a number of structures governs how the final material behaves. So by a more formal definition, we get a bit into electrical properties now. We can define this percolation threshold as a density of filler above which there's a continuous path across a material. So typically, if you have long fibers such as carbon nanotubes, this threshold is about between 0.1 and 1%. And if you have agglomerates, spherical particles, or disk particles, you're more in the order of 1 to 10%. And this is very much a random process. If you repeat the experiment of throwing your structures on a plane several times, you're probably going to see different percolation threshold because it's going to depend on where the structures randomly land. And the path through the material is as well going to be random. But if we look at this case more formally, this is a typical plot of the conductivity of film as you add stick-like conductors to the surface. And below the percolation threshold, before the concentration at which you have enough sticks to create this continuous path, you have essentially no electrical conductivity. Then at the concentration at which you form this first continuous path, the conductivity jumps dramatically. So now it goes from essentially 0 or 10 to the minus 10 Siemens per meter, in this case, to a factor of about 1 Siemens per meter. And then you see after that, as you add more and more sticks, more and more conductors to the network, the conductivity continues to increase. And the percentage at which this transition occurs is what's called the percolation threshold. There are formal ways to fit this curve and decide exactly where you define the threshold. And then the scalability of the conductivity after this threshold depends on other factors. For example, the length of the individual conductors and the contact resistance between them, and so on. But in principle, this idea of percolation is just a geometric thing. When you have enough structures in the right configuration to create this continuous path, this transition occurs abruptly. And you might see different transitions, different thresholds, depending on the characteristics, for example, the length of the structures that you put on. So the most general model for this percolation behavior says that the conductivity scales according to an equation like this above the percolation threshold. So you have a conductivity which is equal to some assigned maximum conductivity at high volume fractions, and that is multiplied by the density of the structures, or the volume fraction or area fraction, minus the critical density, so the density at the percolation threshold, multiply or raised to an exponent. And if you had a perfect three-dimensional network of structures, like a perfect three-dimensional lattice, the value of that network would be, the value of that exponent would be 2, and practically the value of this exponent varies on a lot of things that we've already mentioned, such as the geometry and the morphology of the conductors and the characteristics of contact between them. But this general kind of equation is often fit to the percolation behavior of networks to determine what's dominating their characteristic transport. And other model, for example, this can be derived by mapping one of these random networks, for example, as a resistor network. And here, you see a case where you've just formed a percolation network across the gap. And if you just map out that each structure has an inherent resistance, and there are also contact resistances between the structures, you can see that you have a combination of serial and parallel paths. And if you added up all the individual nanotube resistances and junction resistances, you could get a final resistance for this network. And by using this in combination with some statistical math, you can derive the origin of that percolation curve and predict how it's that general power law scaling we saw on the previous slide. So this is from the old Balborg paper, which is up for your reference if you wanted to look at it. So there have been some interesting experiments that let us relate the transport properties of networks to the characteristics of individual structures. And now we'll see an example from a paper from a few years ago that studies how the electrical conductivity of a thin film of nanotubes depends on the size of the film. And if we imagine being in the many micron or millimeter scale regime, you could say that, well, it's just going to behave like a film of metal, where the conductivity or the resistance, the conductivity is going to be the same, and the resistance is going to scale by Ohm's law based on the length and the thickness. And that's right. However, if we are, for example, in a regime where the density of nanotubes is low, or where the distance between the two electrodes is comparable to, say, the mean free path of electrons in the nanotubes, we see different aspects of scaling. We, in fact, see a combination between the quantum size effects of the nanotubes and the classical size effects due to the interactions between them, essentially between the structures and their boundaries in this network structure. So if we have a narrow gap between the two electrodes, we're more likely to be in the ballistic regime. And if we have a wide gap between the electrodes, we're more likely to be in the diffusive regime. And so here, L sub C corresponds to the gap between the two electrodes, and LS corresponds to the average length of the nanotubes, or the length of the fillers. And in general, in this case also, the resistances between the junctions, between structures in contact, are way larger than the intrinsic resistances of the structures themselves. So in a first case, what they did is they looked at the case where they had a low density of nanotubes in this material. So they had a case where the density was below or near the percolation threshold, so there was a very strong dependence of the conductivity on the density of structures. And they varied the length of this channel, of the gap here, relative to the mean free path between, or the mean free path of conduction through the nanotubes. And so if they had, and they were doing a bunch of other things here, like varying the length of the nanotube, so they could change this value of LC divided by LS, where LC is the length of the device and LS is the length of the nanotubes. But for example, if we're in a geometric regime where we have a large mean free path, you can see that the conductivity is not varying so much as you change the gap of the device. And if we're in a regime that's more diffusive and is beyond the mean free path of the structures, then the conductivity is going to decrease more as you increase the gap in this device. And here we're just seeing the current. So if the current is higher, then the conductivity is higher. So as the device gets wider, the conductivity drops because there's more material and therefore the resistance is higher. But certainly without further details, here you see that the scaling behavior is different, and at the limit of having a small gap between these two and a large mean free path, you can actually conduct ballistically across this network. And you have a large number of nanotubes spanning the gap, and you're issuing ballistic transport through all of the nanotubes in parallel. If we look at the other limit, and we don't need to follow all the details on this slide. The paper has a lot of very nice results. But now they look at a case where they have a very, very high density of nanotubes. So they're way beyond the percolation threshold, and you have essentially a thin film of nanotubes at a high density. And they have a case where the length of the channel, L sub c, is much longer than the mean free path. So now we have essentially a ribbon of nanotubes that's many, many microns long. And they see what you should expect, that if you look at the exponent, the conductance exponent on this percolation type scaling, you have an exponent of 1, which says that the conductivity is scaling linearly with the length, and we're essentially following Ohm's law. So we can go from the case of ballistic transport through one nanotube or many nanotubes spanning the gap to the case of essentially regular ohmic diffusive transport dominated like a bulk thin film if you have a large number of contacts and a large spacing between the electrodes. And between those regimes, exact issues of the geometry and the topology are going to tell you how this scaling varies precisely with the number of contacts. But for example, if you could engineer the film so it had a very low percolation threshold, you might be able to create a more effective composite that could provide that conductivity necessary for electrostatic discharge at a very low volume fraction of fillers. And I'll just flash over these slides to show the generality here that this general behavior of percolation is observed in other systems as well. For example, in composites of silver nanowires and polymers, kind of the same type of thing, except here we're looking at resistivity and not conductivity, but there's a percolation threshold that's crossed when the conductivity goes from one value to another value. So here they're adding nanowires and we're not really forming a continuous network, and then boom, a small change in the concentration gives a big increase in conductivity. Same thing here observed with copper nanowires and polystyrene as a matrix. Likewise for nanoparticles, in this case, the trend looks more shallow, but we do see a pretty abrupt transition in conductivity when we're filling this material with antimony-doped tin oxide, a semiconducting particle, onto a substrate. So this general idea of percolation, of forming a continuous network, applies to structures of a whole bunch of different materials and sizes and geometries. And the precise value of that transition is going to be determined by the geometric case that we're interested in. And this is also observed in the example we saw several lectures ago, where nanotubes were functionalized and mixed with polymer particles and then combined and made into a composite film, like so. And this is just the picture that shows the surface of the network where you had carbon nanotubes dispersed in the polymer, and the electrical conductivity of these was measured. So now we see again the slide that I showed to initially describe the conductivity of a percolation network. And this is actually data from that nanotube polymer composite film we saw on the previous slide. And we can see that the concentration of the polymer nanotube film increases by this percolation law. And in fact, we see different behavior for nanotubes that are made by two different processes. In the first case, this data, which shows a relatively low percolation threshold, comes from nanotubes that were taken from a vertically lined forest and dispersed and then mixed with the polymer and then made into this film. And in the second case, the nanotubes were taken from a commercial powder, nanotubes that were first made as a tangled mess and then issued through this same dispersion process. So in the forest, the nanotubes are initially very long, and the dispersion process actually cuts them up into smaller pieces, but it turns out that the nanotubes that come from the forest and end up in the polymer are longer than the nanotubes that come from the powder that wasn't initially aligned. And so that's one reason why the percolation threshold for the longer nanotubes is lower than the percolation threshold to the material with the shorter nanotubes, as well as the final conductivity that is achieved as you increase the volume fraction beyond the percolation threshold is also higher. And another attribute that was found to be important is the intrinsic structural quality of the nanotubes made by those different methods. This plot shows a thermogravimetric analysis, meaning taking the material of nanotubes, just the nanotubes on their own, and heating them and watching how their mass decreases as a function of temperature. And we see that the right curve corresponds to the nanotubes from the forest, and the left curve corresponds to the nanotubes from the powder, and the ones from the forest have a higher decomposition temperature, which generally indicates that they have fewer defects and are of a higher structural quality. So in principle, this is telling us that that higher conductivity in the final case beyond the percolation threshold is also influenced by the fact that those nanotubes had a higher intrinsic structural quality. Incidentally, the nanotubes from the forest also had a higher content of amorphous carbon that burns off at lower temperature, in fact about 10%, whereas the industrially made nanotubes were a lot purer, but the conductivity of the forest nanotubes was was nevertheless higher in spite of this difference. So here's an example of a case where those two differences in network properties based on two types of nanotubes might be related to other characteristics of the material using other characterization techniques. And another interesting and useful attribute of these thin films is that they can be transparent. And this shows an example from work from several years ago, the first paper that was published on nanotubes as transparent conductors. And if you have a very thin film of nanotubes that is electrically conducting, it, of course, doesn't have a very high volume fraction, so you can, in fact, still pass light through the film and pass electricity through it. So there's significant work on development of processes for making high conductivity, uniform thin nanotube films also as transparent conductors for applications as touch screens, for phones and things like that. And you need a relatively high conductivity as well as a high transparency, and these are trying to compete with indium tin oxide and other materials which are the standard. And for example, from a characterization point of view, there's interest in looking at the transparency of the films over wide wavelength ranges. And the visible range might be what we're concerned for, say, personal electronic devices, but applications in the IR and other wavelength ranges might be also interesting for other thermal properties or communications applications. And in fact, the interaction of light with light of a particular wavelength with the material is in fact then related back to the electronic structure and the characteristics of the nanotubes themselves. If you had, for example, semiconducting nanotubes, then you could find that they absorb at a certain specific wavelength that corresponds to the band gap of those tubes. But these kinds of networks are ensembles of nanotubes of metallic and semiconducting characteristics, so they kind of have bulk properties. And incidentally, more recently, there's been work on separation of nanotubes like we saw by the centrifugation process. And there, if you deposited a thin film of nanotubes of a particular chirality and therefore a particular band gap, you would essentially have a color filter. You would have, say, a thin film of a certain color where that color corresponds to the band gap of the nanotubes of that particular chirality. And depending on the thickness of that film, you would be able to change the transparency of it and the conductivity of it. So there are some more interesting materials that are being built upon this principle. So I want to give us a bit of time to move on to the other topics, but if you get to look through these slides yourself, you'll see a couple of other applications. For example, using these nanotube films as strain sensors, where if you have films of different percentages of nanotubes inside a flexible polymer, as you stretch the material, you essentially reverse the percolation behavior. So imagine taking a network and pulling it, so you're pulling the nanotubes essentially farther apart. And if as you pull the network, you're sliding the nanotubes over one another and then maybe eventually pulling the nanotubes apart, there'll be a critical strain at which you essentially break this network. And when you break this network, then you'll have a very high sensitivity to strain because you're going over into the regime where there isn't percolation through the material. But by and large, even though there's been work in preparation of a lot of these assemblies of structures, of electrical assemblies of nanotubes, for example, the properties of these networks are still far beyond the properties of bulk materials, of individual nanotubes, or, for example, of copper. So to close this section, this slide plots the conductivity of these particular materials as a function of the packing fraction of nanotubes. So the same thing as volume fraction as we saw before. And the red curves represent the conductivity of copper, and copper is a bulk material, so the conductivity of copper isn't going to depend on the volume fraction, and the different red lines correspond to different widths of copper wires. So this is essentially the conductivity of bulk copper, and the conductivity of copper goes down as its size goes down because of grain boundary scattering. And this is, in the end, meaning to compare the properties of individual carbon nanotubes to the characteristics of small copper wires for the application of electrical interconnects. And we can see that individual nanotubes have been measured to be as conductive or more conductive than copper wires of certain sizes. So if you have a short nanotube that's in the ballistic transport regime, you have a very, very good conductivity if that is a very high-quality nanotube. However, by and large, all different methods of making networks of nanotubes have failed to even get within 2 orders of magnitude of the bulk conductivity of metals. And we could look into the different methods by which these were made. For example, these are very small pillars of vertical nanotubes that are made by Fujitsu. I think we saw this in the lecture on electrical properties before, the vertical interconnects. These are horizontally aligned ribbons of nanotubes made by growing forests and knocking them over. But in all these cases, efforts that try to pack large numbers of nanotubes into small spaces so far fail to approach the bulk properties of metals. And so this is a real challenge for example, using nanotubes in electronic applications where you really need high conductivity transport across small spaces. So I think there's certainly a lot of work to be done in here, and these deficiencies relate to the intrinsic flaws in the nanotubes as well as the inability to pack them into very high density oriented configurations. But if we could, get a bunch of individual structures that all had short distances and ballistic transport across them, it shows in principle that you can achieve the bulk conductivity of metals in these particular cases. So the inability to scale the properties of nanotubes is not that they don't match with theory, but that organizing them in precise ways is the real limitation. So now let's move on to talk a bit about the thermal properties of networks. And in the case of thermal properties, we see dominance of phonon-phonon scattering at the interactions at the interfaces between structures. And that's what really dominates the properties of a network. Because we saw before that, like for electrical conductivity, the thermal conductivity of nanotubes is very, very high. It's been shown to be 2,000 to 3,000 watts per meter Kelvin, even when you are beyond the mean free path of phonons in the material. However, at a macroscopic level, we would think of transport between interfaces being dominated by thermal contact resistance. We need to think of a similar thing at the nanoscale. So here is just a snapshot of how contact resistance is formulated macroscopically. If you take, for example, 2 copper blocks, 2 copper surfaces, and measure the heat transfer between them, the thermal conduction is going to be dominated by the roughness of the surfaces. And while we could say that we, for example, have 2 square centimeter parts in contact, the true contact area is actually determined by the areas where the peaks of the surfaces line up on each other. And that means that the contact resistance depends on the number of these areas and the pressure that's applied, and that affects the heat transport through the interface. And if you looked, for example, at the temperature gradient through the structure, you could see that in the bulk, the heat is transferred very well. And at the interface, the heat is transferred not so well. And then as you get into the other bulk, the heat is transferred a lot better. And the same thing essentially happens when you have two nanostructures in contact, two carbon nanotubes. The heat is transferred very well along the nanotubes, but the heat is transferred by a significantly poorer margin at the interface. And the mechanical conditions of the contact between the two nanotubes determine what this local temperature drop, if you can really define, the concept of temperature there, is at the interface. And we won't get into specific ways that this contact resistance is formulated, but if you were to look into the extra slides, you'd see some snapshots from this paper that does a simulation, a molecular dynamic simulation of the effects of the length of nanotubes and the distance and characteristics of overlap between them on the total thermal transport through this kind of assembly. And what they do is they hold the ends of the opposite nanotubes at different temperatures, and as a function of the distance of this overlap and the spacing between the nanotubes, they plot the temperature profile between them. And you see here, kind of like we saw for the bulk interface, there would be a temperature drop at the interface determined by the characteristics of this contact. And indeed, what they do is they start from fairly intuitive and simplified way to create a molecular formulation for this contact resistance. So effectively assume that the behavior of the carbon-carbon bonds is dominated by this Leonard-Jones potential. And so if you have a particular spacing between two nanotubes, then the vibrations between one nanotube and the other, according to the temperature, are coupled by the transfer of vibrations across a small gap. So if one atom in one nanotube is vibrating, it is effectively feeling the other nanotube if the other nanotube's atom is within a distance that gives sufficient van der Waals interaction energy. And you could look at the paper to see how this is formulated in detail. And as you can imagine, that would predict that the contact resistance between the nanotubes dominates the transport, and also the transport is also affected, for example, by the spacing between the tubes. There's a big difference if there's a 1 nanometer gap or a half nanometer gap versus having the tubes in good contact. So in terms of experimental results, there have been a lot of studies characterizing the thermal conductivities of nanotube assemblies. And for example, here is a snapshot from an experiment that uses an IR technique to measure the heat transfer through a suspended film of nanotubes. So you can imagine here they perhaps use one of the vacuum filtration techniques to create a thin paper. And then they suspend it in a chamber where they resistively heat it. They pass a current through it, and then they use an IR camera to measure the thermal emission and therefore calculate the power that's emitted by resistive heating of this material. So then by knowing the resistivity, the resistance versus temperature, the power dissipation, and the thermal emission, they can get a measure of the thermal conductivity of the assembly. It's what's called bolometry. And their results, you can see here, there's a picture of their apparatus where this ribbon of nanotubes is suspended. And what they see is they measure the conductivity of this mat of nanotubes. So K is the thermal conductivity in watts per meter Kelvin as a function of temperature. And so if we look at the case over here, which is at room temperature, you see that the thermal conductivity of these mats is between, say, 10 and 100 watts per meter Kelvin. So it's about a factor of 10 to 30 below the conductivity of the individual nanotubes. And they, in fact, compare the conductivity of nanotubes that are AP or as prepared and nanotubes that are purified. So in the case where they've purified the nanotubes to, for example, remove residual catalyst and amorphous carbon, the thermal conductivity of this film is quite higher. And they do another measurement where they calculate what's known as the Lorentz number, which is a measure which suggests the relative roles of phonons and electrons at being responsible for conduction of heat. And so it's calculated by dividing the thermal conductivity, kappa, the value from the top graph, by the electrical conductivity, just measured by the resistance of the film, multiplied by the temperature. And we can see here now that actually in this case of having single-wall nanotubes where some of them are metallic, say a third to a half of them would be metallic, in fact, electronic conductivity is dominating the thermal transport. So this value of this Lorentz number is between 10 to the minus 4 and 10 to the minus 6, which says that electrons are carrying most of the heat through this material. But compared to a metal, which has a value of about 10 to the minus 8, the contribution of phononic conductivity is still higher. And I think it's interesting here that the value of this number is lower for the purified nanotubes, indicating to me that the purification process is, for example, causing perhaps more structural defects in the nanotubes, decreasing the electrical conductivity, but it is increasing the ability of the nanotubes to transfer heat by phonon transport and perhaps therefore cleaning up the sidewalls. So if you have stuff on the sidewalls of the nanotubes, that can play an important role in phonon scattering, perhaps more so than electron scattering, and that could be why the purified nanotubes show a higher phononic thermal conductivity relative to their electrical conductivity. But by and large, the lesson here is that the net bulk transport is way less than those of the individual structures that might be measured. Now, another technique that might be used to measure the thermal conductivity of a material is just like the same kind of setup that is used to measure like the conductivity of, say, a piece of copper, where you take, this is according to an ASTM testing standard, you take two vertical rods and you press them together and you pass a certain amount of heat through the rods, and you measure the temperature profile across this apparatus. So it's kind of like measuring the temperature across the interface we saw before. And by doing that, you can measure the thermal resistance of a material that you have in the gap. And this is often used to measure the thermal conductivity of forests of nanotubes and also of things like gels of nanoparticles that are kind of made into pancakes and put at this interface. And for this is really more of a bulk measurement. But this, for example, has been used to measure the conductivity of a film of nanotubes if you squash it really, really, really tight. And in the case of electrical transport, we saw that in all the instances we saw, if you increase the packing fraction of nanotubes inside the material, you get a higher electrical conductivity. But what this study shows in the case of thermal transport is that's not always the case for thermal conductivity. So what they did is they took a powder of nanotubes bought commercially, and they made it into a little chunk. They took a chunk of powder, and they put this chunk of powder between the two contacts in an apparatus like this, and they applied pressure to the material. So they were measuring the transport through kind of this bulk three-dimensional network of nanotubes as they applied an increasing mechanical load on it. And they saw that under these cases where you had a lot of pressure and a high density of nanotubes, so a lot of contacts, you had extremely low thermal conductivities. So here's a case where if we take any of the three rows here, they compared nanotubes of different diameters, single-walled and multi-walled and so on. They had about 20% nanotubes in this material. And in all of these cases, they were applying pressure of, say, 1 to a few atmospheres. And they had thermal conductivities that were less than 1 watt per meter Kelvin. So a typical polymer might be 1 watt per meter Kelvin. In the previous slide, we saw the film, which was a looser network of nanotubes, maybe 1% nanotubes that had, say, 100 watts per meter Kelvin. And what they found here is that the fact that they were pressing the nanotubes in such tight contact, having many, many tubes in contact with many, many other tubes, means that they gave so many opportunities for phonon scattering that they significantly decreased the thermal conductivity of the net material. So they essentially took a case where if you pulled out any one of these nanotubes and suspended it itself across a gap, you would have a thermal conductivity of, say, 1,000 watts per meter Kelvin or higher. But if you take a huge number of them and you slam them together in a densely packed powder, the effect of scattering between the tubes of essentially deflection of those vibrations renders the net conductivity lesser than a regular polymer would have. And in fact, they went a bit farther, and they proposed the idea that, sure, if you have a junction between two nanotubes, then there is some thermal conductance of that junction, which dictates how much heat goes across, and the same ideas of like spacing and communication that we saw before. But in fact, if you had a case where you had one nanotube in contact with two other nanotubes, if you had two contacts onto that nanotube within a distance that's smaller than the phonon mean free path, there was a significant decrease in the thermal conductance of this tube. And this is saying, for example, by their simulations, that at room temperature, the conductance of a case where you have two contacts essentially trying to block the phonon transport along the nanotube is 10% of the case where you had one contact. So what I mean here and what they mean here is, imagine you're trying to shove heat through this nanotube and you have these other nanotubes pressing on it kind of as rails. The effect that you're mechanically contacting the outside of that tube, even though you may not be transferring heat through here, is affecting the thermal transport through the tube itself. So just this physical constriction of the vibrational modes in the material was causing a dramatic decrease in the thermal conductivity. So in this case, you have this three-dimensional network of thermal conductors where you're trying to get heat from one side to the other, and no matter where the heat is going or can go, the fact that it is in contact with a whole bunch of other tubes is dramatically decreasing the ability of the material to transport heat. And this is another kind of limiting case where we see how the scaling of properties is very different as we get to large number densities and particular length scales. So I'm afraid we only have a few minutes left, so I probably won't get to talk about joining of structures, but in the interest of moving on to the last topic next time, I'll leave those slides just for your reference. And now I'll just try to show a couple slides about mechanical properties that get to the point. And the point is that it's possible to enhance the mechanical properties of materials such as composites by adding structures. But if we use the example of nanotubes again, we see significant limitations due to the orientation and packing fraction and alignment of the structures. And it's a lot easier to get a great stiffness than it is to get great strength. And there's, for a long time, there have been studies of mechanical networks. For example, paper is a mechanical network and a nanofibrous network because it contains essentially natural biological filaments derived from wood pulp that create a tangled material that can transmit load. You can hold quite a lot of load on a piece of paper. And the mechanical characteristics of papers have been studied for a really long time. This is a paper from 1952, and they're looking at the modulus of the material as a function of the fractions of fibers that are aligned along particular directions. And I'm showing you this because, by and large, the same mechanics can be applied to modeling the mechanical properties of networks of structures, except now we maybe know a bit more about the properties of the individual structures and the properties of the joints between them. So if we looked at a model of a mechanical network, we could consider it as an assembly of kind of randomly placed beams on a substrate. And we could reduce a network like this to a network where we only, say, identified the continuous load paths within the structure. Because now, we don't care about maybe there's semi-contact, there's close proximity. We're only going to transmit load through the places where the structures are actually hooked together. And then this could, for example, be related to a model of the structures that considers their individual stiffness and considers the stiffness and the characteristics of the joints. So, for example, if we looked at one joint, there's been work, as shown in one of the readings, where you consider the nanotubes as individual beams, and you consider the connections between them as springs with particular characteristics. And if we thought of having a polymer at the interface between the two structures, we would have an assembly, and we could use, for example, quite traditional mechanics to consider the effective stiffness of this assembly. And you're certainly welcome to read this in more detail if you want. But what I wanted to jump to is a bit of discussion about the properties of assemblies of nanotubes in tension. So you could consider that, if you had a paper of nanotubes, then the stiffness might be higher if you have longer nanotubes or stronger connections between them. But really, one of the dreams of scaling up the properties of nanostructures is the strive and the effort to make, for example, continuous cables of carbon nanotubes that have properties that relate to the individual structures. If you could do that, we could make fibers that would be 10 times as stiff or 10 times as strong as carbon fibers. So, like, in an effort to do this, the properties of nanotubes taken from forests were recently studied. So, for example, a nanotube forest of a few millimeters high was grown, and they took a pair of tweezers and peeled out a little piece of the forest. So in principle, you're peeling away a continuous strand of nanotubes that has some alignment and mounting it in a frame. And this is actually a typical way that small fibers are tested. You mount it on epoxy inside a paper frame, and then you cut the frame open, so when you put it in the tensile testing machine, you're just applying load to the fiber. And this is maybe a fraction of a millimeter in width and a couple millimeters in gauge length. This is an optical picture of one of the nanotube fibers under test. And in addition to measuring the mechanical load versus displacement, the electrical resistance was also measured, because if the structures are electrically conductive, maybe measuring the resistance versus load would give an insight as to how the material fails. So for this continuous strand of nanotubes, this plot shows the specific stress, and these are in units of newtons per tex, which is the same as gigapascals. It's just you measure it as as load divided by mass per unit length, which turns out to stress divided by density, and versus the strain applied. And we see that this fiber fails at a stress of about 0.1 gigapascals, which is maybe 2 to 3 orders of magnitude beneath the expected strength of the individual nanotubes. And the resistance increases gradually before the fiber fails. And the fact that the resistance increases gradually indicates that this kind of long strain behavior of the nanotube assembly is governed by accumulated failure of the individual nanotubes in this strand. And this is very far from the highest strength that's been measured for yarns or cables of nanotubes, but suggests that the load transmission between the tubes and the straightness of the tubes is really important for getting that high strength characteristic. And so far, a lot better results have been achieved by spinning nanotubes directly into yarns. So for example, creating a dispersion of nanotubes and then using a fluidic process to spin out a fiber, as might be done for something like Kevlar, or for example, in work done at University of Cambridge and other places, having a directed furnace that creates essentially a jet of nanotubes and lets them be spun into a thread, facilitates the manufacturing of threads of nanotubes where in principle the nanotubes are relatively aligned. It's kind of like a yarn, only instead of having cotton fibers you have carbon nanotube fibers. And in this case, by making nanotubes that are much higher quality than were in those forests, they've been able to achieve specific strengths of about 10 newtons per tex, or about 10 GPa in the best cases, which is about a factor of 10 beneath the stiffness of individual nanotubes, or the strength of individual nanotubes. But in fact, what they see is they see a bimodal distribution of strengths as a function of the gauge length of the specimen they apply. So the gauge length means how large the gap is between their loading axes. So taking a piece of yarn and grabbing it across a 1 millimeter gap versus a 20 millimeter gap. And what they suggest is that the highest strengths occur when they grab the yarns with a very, very small gauge length. And they believe that that is a case in which they are connecting a large number of continuous nanotubes across the loading gap. And when they have a larger gauge length, the strength is lower because their strength is dominated by connections among nanotubes that are trying to grab each other by shear. So this is suggesting that perhaps the only way to push the limit of the strength of nanotube assemblies to very high values, and maybe 10 to 100, is to really make continuous, perfect long interconnected nanotubes. And these yarns are not perfectly straight. The nanotubes are twisted and somewhat tortuous. So that is another thing that would need to be improved. So in the case of mechanical properties, these these yarns over very, very small fibers are maybe a bit better than carbon fiber now, but still way worse than individual nanotubes. But if we consider the bulk characteristics of these fibers, carbon fibers that are more continuous over long distances are still better than nanotube assemblies. So time is up, and I'm sorry we couldn't get through everything for today, but I hope this was just a little overview of some of these topics.